Swayam Prabha. Digital India. Educated India.
Welcome back to lecture number 21. Let us continue with the same topic, heat load components, under part 2. So in lecture number 21, part 1, I had stopped at this point estimating the product load, which is the sum of 4 heat loads, that is Q1, Q2, Q3 and Q4. Q1 is the sensible heat load above freezing, Q2 is the latent heat load, Q3 is the sensible heat load below freezing, and Q4 is the load due to respiration. Let us see the next heat load, infiltration load. So as I had explained in the previous lecture, infiltration, it is nothing but the leakage of air through air cracks, air gaps, door openings. The door opening, especially at the time of the product being loaded into the cold room, and also due to the during the time of the movement of the products. So this air leakage can be through the walls, ceiling or the roof, floor, etc. The leakage of air contributes to both sensible and latent heat load. Normally the temperature portion contributes to the sensible heat load. The moisture portion of the air, that is the water vapor present in the air, it contributes to the latent heat. Here I have given a formula to calculate the velocity. So that is V equal to 0.06 into H into delta T. Here H is not the enthalpy, H is the height. H is the height of the door. So this is based on the particular component of the cold room, that is the door, because this load comes into picture when the door is opened and it is until it is closed. Even otherwise also there are chances of, if there is some porosity in the wall construction, there is some porous nature, there are chances of air getting circulated into the cold room through the gaps. So the infiltration load is represented by the letter QI, QI, Q suffix I, capital letter I. So here I refers to infiltration. So this is equal to rho into A by 2, density into A by 2 into velocity into H2 minus H1. That is enthalpy difference of the air. So here A by 2 is A refers to the area of the door. So that is half the area is considered. Half the area of the door is considered. So A is the area of the door. That is only half the area is considered. That's why that it is divided by 2. V is the velocity, rho is the density of air, which we can take it as 1.23 kg per meter cube. So rho is equal to 1.23 or 1.2 kg per meter cube. A by 2 is represents the half area of the door. Half area of the door, and V is the velocity H2 H1 or the enthalpy of air which is present inside, and the enthalpy you have here which is present outside. It is in kilojoule per kg. So here H refers to height, not enthalpy. Okay, so let me write it here also. So H1 small h refers to enthalpy. Let me write the velocity formula also on this side. Velocity is equal to 0.06. Let us see the formula. 0.0606 into h into delta t, that is square root of 0.0606 into h into delta t power half. So this is nothing but 0.0606 square root of h into delta t. Square root of h into delta t. Capital H is door height. Door height in meter. So this is enthalpy. So since h is used, normally the learners will tend to assume it is as enthalpy, because we use enthalpy, small h for enthalpy, small s for entropy, etc. So this is the formula which is used to calculate the infiltration load. Next one is the ventilation load. Ventilation air is admitted inside the cold room to maintain the desired air quality inside the room and to purge unwanted gases periodically. To purge unwanted gases periodically. Okay. Ventilation air is admitted inside the cold room. So again, here also there is one small correction. I have used the infiltrations, but sometimes when we are calculating the infiltration load, so the ventilation load is also will become a part of it. So sometimes it is used Q suffix V, sometimes it is used Q suffix I. So here I have used the same representation, that is which is used for infiltration. So rho into V into H2 minus H1. Qi is equal to rho into V into H1 minus H2. Okay, H2 minus H1. Okay, H2 minus H1. Let us take this as ventilation as QV, otherwise it will be confusing. So let us take this as ventilation load. QV represents ventilation load. So here also let me write it like that. So here rho again is the density of air, which is equal to 1.23 kg per meter cube. This is V, QV. The eraser is not functioning, I think. This is QV. Okay, so this is QV. Heat load due to ventilation. So here V is volumetric flow rate of air. Volumetric flow rate of air. That will be in meter cube per second. So if you see the one, V is the volumetric flow rate of air. It is not velocity. If you know the area and the velocity, the basic formula is volumetric flow rate is equal to velocity multiplied by the area. So that is, area is in meter square, velocity is in meter per second. So when we multiply this term, you will get meter cube per second. Meter cube per second. So this is nothing but area into velocity. So this is meter square, this is meter per second. So we will get the in meter cube per second, which is equal to meter cube per second. So V equal to area into velocity. So again here half the area is considered, half the area of the H2 is the enthalpy of outside air and H1 is the enthalpy of inside air. So this is H2 minus H1. This is how the ventilation load have to be evaluated. Other loads comprises of equipment load, occupancy load, lighting load and lighting load. So equipment load, primarily the fan motor, the motor of the fan that is used in the cold room, which contributes to the major portion of the equipment load. Occupancy load, that is the number of persons or people, those who are working inside the cold room. So this occupancy load can be calculated using the tables which are as per ASHRAE or ISHRAE standards. I will be using those tables. Even the fan motor load, the kilowatt, the rated kilowatt, the motor kilowatt, rated kilowatt will be given. How much kilowatt it is connected to the refrigerated space, that can be taken from the value can be taken from the tables from the ISHRAE or the ASHRAE handbook. So I will be explaining that one when we are solving the numerical question, which is the design of the cold storage for positive as well as for negative temperature application. The occupancy load can be calculated using this formula. Q naught, occupancy is Q naught O, capital O, that is 270 minus 6 into T. So if you want, we can take lighting load. Typical storage requirement for light intensity are 7 to 10 watts per meter square. So for 1 meter square area, the light intensity in the range 7 to 10 is selected. Let us solve some numerical questions based on the heat load components one by one. So first one is, this is the first numerical question. Determine the transmission load for a store with the data given. The dimensions of the store are given: 10 meter by 6 meter into 3 meter. Insulation material is extruded polystyrene, that is EPS. Thickness of the insulation is 125 millimeter. The outside design conditions are given: 40 degrees centigrade dry bulb, 25 degrees centigrade wet bulb. And inside design conditions are 4 degrees centigrade and 75% RH. So if you see the outside design condition, the dry bulb temperature and wet bulb temperature are given. So just for recollect, what in one of the lecture we have discussed about the psychrometric chart, where I mentioned if we know any two properties of the air, we can find the remaining properties. So here dry bulb temperature and wet bulb temperature are given. So we can find out the condition of air using the psychrometric chart. And once that point is fixed, we can read out the values of enthalpy, dew point temperature, specific humidity, specific volume, etc. Let us solve this problem. So this is the table 2.1 which I have taken from the ISHRAE Cold Storage Design Handbook or Guidebook, which is normally used in the industry while designing the cold storage. Let me make one thing clear. Source of data for the ISHRAE Cold Storage Design Guidebook or Handbook, which I am using for referring various tables, the source of data for this is from ASHRAE Handbook. So primarily ISHRAE is the Indian Society of Heating, Refrigerating and Air Conditioning Engineers, and ASHRAE is the American Society. Otherwise, both the professional bodies are focused on HVAC. So sometimes I may be referring using the word ASHRAE Handbook, but otherwise all the values from the different tables are taken from ISHRAE Cold Storage Design Handbook, for whose source is ASHRAE Handbook. So this difference I would like to mention it at this point. So here if you see this table, there are 3 columns. The first one is the insulation material. This is the table 2.1, thermal conductivity of insulation material. If you have a look at the problem, the insulation material is mentioned, thickness is given, thermal conductivity of the material is not given, for which I will be using this table. So the second column and the third column are the values of K, that is thermal conductivity. In second column, it is given in not in SI unit, that is in British thermal unit, inch, or square feet, degree Fahrenheit, that is inch pound system, IP system sometimes it is called. And the SI unit, the value of K in SI unit is given in the third column. So this is the value of K which is given in SI unit. So this is the value of K. It is in watt per meter Kelvin. So let us solve this problem. So the given data, store dimensions are given. Store dimensions is given as 10 meter into 6 meter into 3 meter, 10 by 6 by 3. So this is normally length into width into height. So that is L is equal to 10 meter, width is equal to 6 meter, and height is equal to 3 meter. So this is height. And the thickness of the insulation material is used is extruded polystyrene . Thickness of the insulation material is given, which is 125 millimeter. So thickness of the given insulating material is given as 125 millimeter. So which is equal to 0.125 meter. Convert the millimeter into. The delta T is the difference between the outside temperature and the inside temperature. Outside temperature dry bulb is 40 and inside the temperature is 4. If it is not mentioned, we have to take it as dry bulb temperature. So 40 minus 4. This is delta T. So let us use the formula which is applicable for the heat load due to transmission, that is transmission heat load. Q suffix T is the transmission heat load, that is equal to U into A into delta T. U is equal to K by X into A into delta T. Now, the K value is not given, which will be taken from the table. I will be going to the table 2.1, from table 2.1. Okay, this is the ISHRE cold storage design handbook. In that book, the values are taken from the ASHRAE handbook. So this is polystyrene extruded. The first one is polystyrene board, that is puff. This is the puff. Second one is polyisocyanurate. Third one is, there are two polystyrene. One is extruded, another one is expanded. The material which is given in the problem is extruded polystyrene, not expanded. So this is extruded polystyrene extruded. The corresponding value of K is 0.035 watt per meter Kelvin. So I will write it here. From ISHRE is Indian Society of Heating, Refrigeration and Air Conditioning Engineers. It's a refrigeration air conditioning society which has its headquarters in New Delhi. So from ISHRE cold storage design guidebook, guidebook. From history cold storage design guidebook. Table number 2.1. So this is the table number 2.1 for extruded polystyrene, which is the given insulating material. K is equal to 0.035 watts per meter Kelvin. K equal to 0.035 watts per meter Kelvin. So the fourth one is polystyrene expanded. The third one is polystyrene extruded. Now we have to substitute the values. So K is 0.035 divided by X is given. That is the thickness of the insulation material, 0.125. 0.125 into area. Area is, we have to calculate the area based on the dimensions of the store. So this is for the 2 into L into H. That is, let me write the formula first, then I will substitute the value so that it will be easy. So K by X into area is 2 into L into H. Sorry, L into W will go by the order. L into W plus W into H plus L into H. So this is area into delta T. Now let us substitute the values. K is 0.035, which we have taken from the table. Thickness is given as 1.125. So 2 into L into W is 10 into 6 plus 6 into 3, W into 3 plus 10 into 3 into delta T. Delta T is 40 minus 4. This is given in the question. Delta T is 40 degrees centigrade dry bulb. That is, and the corresponding inside temperature is 4 degrees centigrade. So delta T is equal to 40 minus 4. If you calculate, the transmission load comes to 2.2 kilowatt. 2.2 kilowatt. Suppose if you are using instead of extruded polystyrene, suppose instead of extruded polystyrene, if the given insulation is material is expanded polystyrene, then from table 2.1, ISHRAE cold storage design guidebook, K value will be, this is just for comparison, I am just doing this portion. Actually, in the given problem, the given insulation material is extruded polystyrene, not expanded. Suppose instead of extruded, suppose if we are using expanded polystyrene, then the K value will be, instead of 0.035, it will be 0.037. That is the value which is given in the fourth row. So it will be 0.037. 0.037. K will be equal to 0.037 watt per meter Kelvin. So in that case, Qt will be equal to, there is only one change in this value of K, other things will remain the same. So Qt will be equal to 0.037 divided by, the thickness is 0.125 into the area, that is 10 into 6 plus 6 into 3 plus 10 into 3 into delta T. Delta T is 40 minus 4. So if you calculate, it will come slightly more than the previous one. So that will be 2.3 kilowatt. When extruded polystyrene insulation material is used, the K value is 0.035 watt per meter Kelvin. As per the dimensions of the store and the delta T, which is given in the problem, and the thickness of the material, the transmission load comes to 2.2 kilowatt. So when the insulating material is changed from extruded polystyrene to expanded polystyrene, then there is slight change, minor change in the K value. Instead of 0.035, it is 0.037, which is very, very small. The difference is very, very small. And the transmission load has increased from 2.2 kilowatt to 2.3 kilowatt. So for keep assuming the thickness remains the same and the other data are same. Just by changing the material from extruded polystyrene to expanded polystyrene, whose K value is not much different from each other, there is marginal difference. So there is a marginal change in the transmission load. So this is the first material which is given in the table is polyurethane board. That is nothing but puff, polyurethane foam. So this is EPS. There are two EPS. One is extruded, another one is expanded. Suppose if you are using a puff material instead of these two, then the value of K is given in the range 0.023 to 0.026. We can take the average value, or you can take the value which is the starting value, that is 0.023. Then again there will be difference in the heat load due to transmission. So with this, I conclude this lecture. Thank you.